Okay, I'm Doug Newcomb. I'm retired, don't work for anybody right now, and I'm full of weird ideas. Fir- Oh, that didn't help. What happened here? Okay, try that. Okay, first weird idea. Lakes and DEMs should be flat. Sometimes I see this, it makes me unhappy. You got triangles across because there's no 3D break line for this when they did the processing with a tin. So, tins and splines, they were designed for sparse data points when you couldn't delineate a water body just by the points. So you had 3D break lines so that you could delineate and set an elevation in the DEM. There's no standard for setting that elevation. It's up to the judgment of whoever does that. So now points have changed over time. We've got the original North Carolina data from 2003. That's all the points, not just the ground points. So we go from several meters between ground points to several points within a square meter. QL1 data, 8 points or more, which per square meter. So we decided to come up with this approach, raster approach. We get the mean ground elevation from the Z values. We do a partial IDW interpolation into the voids that are left. Then we treat the remaining voids as areas to flatten. Then buffer the voids back out to extract the Z values of the shoreline. Then you do stats on the shoreline to get a predicted elevation and variability of that shoreline elevation. So this is Virginia Beach 2013 QL2-ish data. And you can see the voids here for the houses, ponds, the swamp, river, another lake. Now, this is where the voids are left after you do the 3-cell IDW interpolation on the left, and then you come back and buffer from those voids, and you pluck out your shorelines from that buffer using a mask. Then you come back and make reclass your buffer so that you have the void and that shoreline in a single raster, and you clump that so you have a unique ID for every shoreline that's contiguous. Then you run zonal statistics on each one of those plots. So issues, you've got rivers that drain into lakes. And if you do the stats, that shoreline is going to go up the river from the lake. Same thing with dams where the water flows over it. You don't have any ground points on that dam. And then rivers in general, you would like to do something with rivers. Highway overpasses are something still working on. The remedy for a lot of this is 2D break lines, where you just put a line right across where the dam is, put a line on the upstream of the reservoir, walk up a river with 2D break lines so that you have a cascading series of flat surfaces. Highways, we're still working. And so this is the Roanoke River at Williamson, North Carolina. Here we've got our 2D break lines going across the void where the river is. You've got all these other voids in here, and then you've got some building footprints. So the standard deviation of the edge values, you see some variation as you go up the river. As it gets higher, if you've got a higher value in the river, then you can just put in another break line. Split it up. This is what it looks like when you're finished. This is the DEM that comes out, nice and smooth river for the most part. And then this is the DEM that was done without break lines, where you have triangles going across and the river surface varies about a half a meter or more going across there. So the other fun part is that this part of the river is lower than this part of the river. Found out that the bank elevation of the ground points is 20 centimeters below what the USGS gauge says the water level is at the time the LiDAR was flown. So this is also a good way of doing a little QA on your LiDAR. So this tool is published by Dr. Petrosova as R hydroflatten. Current default percentile to use is 5, but based on the data that we've been working through, it's 14 is actually a closer number. And yeah, it scales. 128 billion pixels, coast of North Carolina. This is something I did before I retired. Took about 2.5 days, needed about 2 terabytes of scratch space, but I was able to do it on my laptop, taking data from one USB drive, to the other USB drive to write it out while I was doing my normal work. So it only took about 6 gig of RAM during the entire process. So we've got a reproducible method for creating elevations. Works at landscape scales. It's more accurate than the existing methods. We get to within about 8 centimeters on average of the elevation of the water. And it works on impoundments of all sizes with mostly equal effort. Thanks to these government programs that provided the data, the open source projects that enabled the processing of the data, and these particular folks who helped out a lot.